Hey there, all you cool cats and kittens. For anybody that's been keeping up with the Tiger King store, you'll get that reference. Um, so today I'm coming at you a little different. I'm actually at home today on the front porch. So if you hear some cars going by in the background, that's just something going down the road. But today we're going to be talking about horsepower. So a quick little refresher over some things we've been talking about, because all of these kind of play into what we're doing. Work is distance times force. So if I got a 100-pound weight and I push it 10 feet, that will be 1,000 pound-feet. Sorry, once again, got it backwards. Foot-pounds of work. Power is that number divided by time. So if I do that 1,000 foot-pounds in a minute, then I have 1,000 foot-pounds per minute of power. So you can see the equation for power is actually power equals work divided by time. But another way we can write that, we can explode it out to the work formula. Power equals distance times force, all divided by time. Now the next thing we talk about is torque. So torque, once again, is strength. More specifically, it's a twisting strength. It doesn't always imply motion, but it can. And our formula for that is TO equals F times LA. So once again, if you think back to that chapter 2, we talked about leverage. This is the actual calculation of power that goes along with those leverage calculations we talked about. So if we have this marker that's 6 inches long, and I push at 20 pounds to rotate it, 20 pounds at 6 inches will be the equivalent to 10 pounds at 1 foot. We'll have 10 pound-feet. Make sure we get that one right, because once again we have force times LA. So force times the distance, we're going to use it in that. So pound first, we'll have 10 pound-feet of torque. Okay, so now we're going to move on to our next set of equations and concepts, and that is not writing. Marker's no good. Horsepower. So what is a horsepower? Well, this has kind of got some interesting interesting stories behind it. A horsepower originally is exactly what it sounded like. It was the power of a horse, and I'll give you a little history on this. I'm going to attach a video from Donut Media to this, so shout out to Donut Media, teaching us all about those buff horsies. If anybody follows Donut Media, you'll get that one. But there was a guy named James Watt in, I believe, Scotland back in ye olden days. Not sure the exact year. And he liked doing calculations, and you know, he was a mathematician, something like that. I don't remember the exact story. But basically, he was watching Shetland ponies pull coal and other things out of mines. You know, Shetland pony, for all my horse girls that usually sit up in the front row, you know who you are. He was watching these Shetland ponies pull out coal out of a mine through either pulling up a ramp, or they had a pulley system where the pony would walk straight and there was a pulley and it would wheel it up. And what he basically figured up was that the average pony could pull about 22,000 could produce 22,000 foot-pounds per minute of power. So at this point, that's basically one pony power. Well, he made up, like I said, he took several, measured how much weight it was, kind of come up with a rough average, and that's what he came up with. Well, then he approximated that a horse was about 50% bigger than a pony. It was about 1.5 ponies. So the number he came up with was 32,572 foot-pounds per minute of work. So that was an approximation. He averaged up what a pony could do, said, well, let's multiply that by 1.5 and call it about what a horse can do. And you know what, 32,572, that's a pretty rough number. I'm going to write that up here just for fun. 32,572 33,572. Kind of a rough number. Hope you can see that. So you know what? The heck with it. Let's just round it up to 33,000. So by definition, and James Watt's estimation of an estimation of an estimation, 1 horsepower is by definition 33,000 foot. I don't want to imply dividing there, but it is 33,000 foot pounds per minute. Fantastic. So our equation, if I can write it over here, I need a little more space. Yeah, I can get away with that. Horsepower equals D times F divided by T for time times 33,000. So horsepower equals D times F divided by the quantity T times 33,000. So if you look, it's literally the exact same thing as our power equation. We just multiply the denominator times 33,000. Pretty straightforward, simple math. It's not that much of a draw. So let's work out a problem with this. If we have, say, I don't know, let's make something up. Horsepower equals, we'll say 60 times 550 divided by, say, 1 times 33,000. Okay, so what does this mean? D, this is 60, that is our distance. Now, let me just pause there before I get ahead of myself. For this equation to work, because we have this constant down here, that tells us something. Those of you that have been in my class, you've heard me say this about a couple other equations. This constant, it's always going to be 33,000. That means that these variables have set units. So distance, in this case, has to be in feet. So I'll write this right here. Distance equals feet. Force equals pounds. And our time equals minutes. So what does this mean? This means that all of this has to be 60 feet. If it's 60 inches, the math doesn't work out. You'll get the answer wrong. 550, that's got to be feet. It can't be yards. It can't be miles. It can't be inches. It can't be meters. It has to be feet. Give you a good example. So time has to be in minutes. So if this problem was 60 seconds, then we would have to take that and convert it into 1 minute. Same thing with this. If this said 20 yards, well, we would have to convert that yards into feet, and we would have to do the mathematics in feet. Sorry, there's a neighbor cutting the grass over there. Hope that isn't too distracting. Let's see. So 60 times 550 is, I'm gonna do this problem on purpose to make the math pretty easy. This ends up with 33,000 divided by 33,000 equals 1 horsepower. Pretty straightforward, right? Where did my eraser go? So now let me change this up a little bit and kind of demonstrate how this calculation can change. So the other day, in one of my last videos, we talked on the power calculation video, I showed you 2 tractors, a big tractor and a small tractor. I said if they can do the same work, but one does it faster, the same work is being performed. This equation is going to be the same, but if one does it faster, the time denominator is going to make the math different. So let's say this is, a small tractor. Well, say we move it to a bigger tractor, and instead of taking 1 minute, it takes half a minute, 0.5 minutes. So then what we end up with is HP equals 33,000 divided by, what is that? 16,500 horsepower equals 2 horsepower. So if it does the same amount of work in half the time, it's doing it has twice as much horsepower. If it does the same amount of work in twice the time, it has half as much horsepower. Okay. Now, I hope you understood that, because it's about to get just a little bit more confusing. So, this is horsepower. It's our standard measurement for horsepower, but there are 2 types of horsepower, and we actually use both of these in agriculture. And you'll see what I mean. So, I'm just going to read this little section verbatim that kind of explains it. This type of horsepower is called drawbar horsepower. This is not the type calculated for an engine or rotating shaft. It is called drawbar horsepower since the horsepower requires the drawbar of a tractor to pull an implement. So what does that mean? I have my son's tractor right here, and if we take this tractor, you can see obviously as a toy, this haybine, some call it, cutter crimper, it's attached to the hitch. That hitch is also called a drawbar. So that drawbar means that we're pulling something. So this is the covering a distance. It takes so much power to pull in force, and you can do it in a time. The other type is called shaft horsepower or brake horsepower. So on tractors, this is the horsepower that's calculated by looking at a spinning shaft. So on tractors, this is typically done at the PTO shaft, which we've talked about that in my class. Is that shaft sticking out the back of a tractor that we can use to run anything on a farm, a bush hog, grain drill, a sprayer, all kinds of things. We have a spinning shaft. We can do a lot of different things with a spinning shaft. And those calculations are just a little bit different. Actually, they're a lot different, but I'll show you how those are calculated. These for horsepower, shaft horsepower, I'm going to denote this as SHP, and just to keep us a little different, I'm going to call this, put a D right here for drawbar horsepower, just for now. So the equation for shaft horsepower, hey, if you can see my daughter looking in the window, go away, thank you, love you. Shaft horsepower, the equation for that is TO times RPM divided by 5252. Okay, so once again, we have on most tractors, you have to bear with me on this drawing. Oh, that's horrible. There's some kind of little thing on the dash that looks like this. Maybe it's a light that lights up, and that denotes the PTO shaft. So imagine you're looking at the back of a tractor. Actually, it's supposed to have 6 splines instead of the 5 I drew, but you get the idea. And say it's rotating that way. So the light will light up when the PTO's on. You turn the PTO off, the light goes off. So this is kind of the international symbol for PTO shaft. More of a safety feature to let you know, hey, this PTO shaft is spinning. Don't step off the back of the tractor. But imagine this is the spinning shaft out the back of the tractor. And we measure torque. So once again, kind of visualize. I'll change colors for just a second, and I hope you can kind of see it. We measure from the center of the spinning shaft, say out 1 foot, and say it as, oh, I don't know, 1,000 pound-feet of torque, and we're going to say, pop quiz, how fast is the standard PTO RPM on most tractors? I know some of you got it. 500, that's not a 5, 540 RPMs. Now it can go up, it can go down, but that's just kind of our standard. So what we'll do, we'll take for shaft horsepower, oh, sorry, I don't want to do it that way. I'll write it here where you can use it a little better. So if we solve for this, shaft horsepower equals 1,000 times RPMs of 540 divided by 52. Let's see, we'll work it down. So that ends up with shaft horsepower equals 54. 540,000 divided by 52. And I'm going to be completely honest with you right now. I left my calculator in the house, so I'm going to end on that note. Let you figure out how many horsepower that is. Eyeballing it. We're a little over 100 horsepower. So, like I said, with that, I'll leave it up to you, and I will see you in the next couple of days with our next video that will be over engines. Yep, engines. I'm going to talk about a few kind of the basics. I'm not going to go super deep into the conceptual of it. We've already done that in class, but I'm going to go more into the mechanics of it and the calculations involved in it. So, I'll see you next time.